Hello, it's Professor Todd Elliott, and this video we will look at biasing a silicon diode. So, the diode is the most basic unit of a semiconductor. So from this, we can construct more complicated devices, bipolar transistors, MOSFETs, microprocessors, and all the way up. It all started here. There's quite a few different diode types. There's Schottky diodes, power diodes, pin diodes, LED diodes, varactor diodes. It's quite an extensive list, but today we're just looking at just your plain old silicon diode. In the part that I've illustrated, we see the standard schematic symbol. The line is called the cathode, and the anode is the solid triangle. Physically, the anode looks like it's the end of the diode without a stripe, and the cathode is always the gray or white stripe, and that's how you can identify it. So diodes, this particular one it's a standard power diode. It's typically black in color, but Zener diodes can be kind of blue, gray, pink. Small signal diodes, pinky red. So they're not all black, but just the standard diode, like a 1N, 4001 or 4004, those sorts of part numbers. This is what it looks like. Now sometimes you'll see it here. They've called the positive end the anode and the cathode the negative end. It's okay to think of it that way, but it's all sort of relative to one another. There really is no positive and negative end, not in the way that you're probably thinking of it. So this is the diode characteristic curve. Over here we have the V is voltage and F is forward. V is voltage and R is reversed. I is current and F is forward. I is current and R is reversed. So we have the forward voltage VF, and when the diode is forward voltage, that means then that the anode is positive relative to the cathode. Now, for example, let's assume that the anode voltage was at minus 10, and if the cathode was at minus 10.7, even though we're dealing with negative voltages, the anode is still more positive, i.e. less negative. So that's why I don't like the positive and negative terms, but that's okay. So that's the forward voltage. Now, in order to turn the diode on, I'll just erase this while we're talking. In order to turn the diode on, we need to make the anode more positive than the cathode. And you see where it hits this 0.7 volts right to there? For a silicon diode, that is the standard turn on point, at which point the diode is fully in forward conduction. Truthfully, the silicon diode starts turning on more around 0.55 to 0.6. Do you see this line here? How it's not, there's a curve to it. It starts here at 0. We increase the voltage ever so slowly, and it's slowly turning on. But by 0.7, we assume the diode is turned on. but under all conditions. But in reality, it starts to turn on slightly before that point. So you notice then here, the current goes nearly vertically upwards, and that current has to be limited by an external resistance of some sort to avoid damaging the diode. Okay, so here we have forward voltage and forward current. Over here, we have the reverse voltage, and that means then we make the anode have a negative voltage with respect to the cathode. So the cathode's now the more positive side. It's reverse biased. Ideally, the reverse bias current is 0. So this is the reverse bias current. And you can see here it's basically right to 0 axis. And it hits this point, VBR. VBR is the maximum reversed bias repetitive voltage. It's a data sheet number that the diode can tolerate without being damaged. If you go somewhat beyond that, to see how the current now suddenly increases in the reverse direction, well, that means then you've actually we've broken down the diode, and the diode is going to be destroyed. So in reverse biased, the operating range is really in here, and you don't want to be over in there. Now in other videos, I have discussions on the Zener diode. The Zener diode is constructed to live or be biased in the reverse breakdown region, but that's a Zener diode. It's a different device. Okay, so here we're looking at a forward bias diode. So we have a 12 volt power supply. So this is the positive. Okay. If you're using conventional current flow, and it doesn't make any difference how you want to visualize it, really. The current flows from the positive back to the negative plate on the battery. Okay, so this is the common / ground symbol. Okay, so these 2 points are connected together. Okay, so the current's going to flow like that. Now, I've shown the current arrow going in the electron flow, because that's the way it really goes. But however you think of it, it doesn't matter. When you forward bias the diode, the anode is 0.7 volts nominal, because that's this part right there, relative to the cathode, and the diode flips into forward conduction. Okay, and then you're up here on the curve, and that current is being limited by that resistor. Okay, and that means then if we have a 12 volt DC source, we have nominal 0.7 volts across the diode. That means then the voltage across the resistor must be the 12 minus the 0.7 equals the 11.3 divided by the 1K. Boom, there's your 11.3 milliamps. Change that 1K resistor to 500 ohms, the voltages will be all the same, but the current flow will double. So the resistor limits the diode current. When it's forward biased, the diode has a very narrow depletion region. Okay, and this really, it's because of that's what that is. This is the barrier voltage. Well, this is the barrier depletion region. So literally, it's the 0.7 volts in that gap there. Okay. On the P side, I'm sorry, I'm just doing this with my mouse. Okay, we have holes. What's a hole? A a hole is just a spot where an electron is not. So it has a slightly positive charge. Okay, and these are the free electrons which come from the negative plate on the battery, which is acting as an infinite electron source. Anyway, so using electron flow, because that's the way it really is, and it's easier to explain it this way, the strong negative charge on the negative plate there will, because of opposite charges, right, will drive these free electrons across the barrier, okay, and they will fall into that hole, and then it will recombine and then exit and then go back to the positive plate to complete the current path. So to summarize, a forward bias diode has a nominal 0.7 volts between anode to cathode. The cathode is 0.7 volts negative with respect to the anode, or the anode's 0.7 volts more positive than the cathode, just looking at it from two different sides. The negative plate on the battery has a strong negative charge. It will repel the free electrons in the doped N region. It's doped to have free electrons, which will be enough to kick that electron up out of the valence band into the conduction energy band, where it will go through the barrier, the depletion region, and then it will lose its energy, recombine, fall into a hole in the P region, and exit the P region to become the current, to complete the current path. Okay. All right. So that is essentially how it works. Okay. So we have the same circuit. Notice I interchanged the difference between the positions between the diode and the resistor. Doesn't matter. Nope, because you're still in series. There's all the key calculations for you. Okay, reverse bias diode. So I've simply turned the diode around. So the cathode terminal is facing the positive terminal on the battery. And because of that, the diode is reverse bias. It's essentially acting like an open switch. So the current is going to be 0. In reality, it's going to be small microamps. That's called the reverse leakage current, or just simply the leakage current. Notice the depletion region here is very, very wide. That's because the reverse bias voltage widens that region, and that's what's making it difficult for the current to flow, for the electrons to pass through. And the odd one will, but 99.9% will not. And that's why the current is very low. Okay. There's all the key formulas. Notice that when it's reverse biased, cathode is facing the positive on the plate, so it's reverse biased. This diode resistance is theoretically infinite. It is not, but if it was infinite, right, and this was 12 volts, then this would be 12. Okay, and which I have marked there. And that means then the voltage across the resistor would be 0 and the current is 0. Practically speaking, if this is 12 and this is 0.7, and it probably won't be exactly 0.7 if you measure it, could be 0.68, 0.72. Remember that 0.7, there's nothing magical about it. That's just a nominal, typical, average value when it's turned on. Okay, when it's reverse bias, it's acting like an open switch, so it has a high resistance. Okay, all right. But if you pull 10 diodes out of a bag and test them forward and reverse bias equally and put all the data in a chart and average them, you would get a good handle on what the number should be. But there is some variances. But anyway, practically, if this is 12, again, sorry, I'm just doing my mouse here. If that's 12, this is probably 11.9. 99 to 11.98, something like that. So that means the voltage here would be 0.1, 0.2, okay, and the current would be just a few microamps. So again, my earlier statement that the reverse bias diode, all of the source voltage appears across the diode, and the current is 0. It's not literally true, but it's more or less the case. Ooh, diode models, ideal diode, okay, ideal diode, there's no turn on voltage here, so what we're saying is then this then turns on right there, okay, there's none of this, okay, right, so ideally then the diode turn on voltage forward biased is 0, which in this case would mean all of the source voltage, the 10 volts, is across the load. But because of the internal dynamic resistance, I'm sorry, it's a little small, R prime D, there is a little bit of voltage resistance internally, and that accounts for that 0.7 volts. Okay, drop. So this is forward biased, again reverse biased. Ideally this is infinite resistance, okay, so then all the voltage falls here. In reality, if we model, there's a high resistance in parallel with the diode. This is sort of the mathematical model, and the voltage is more like 11.99. But okay, but anyway, I hope that gives you the idea. Okay, I got it from here, so credit where it's due. This is an LED. You've seen them all before. This is not a high power LED. This is just your standard LED, like on your remote control or whatever. They come in different colors. The color determines the turn on voltage. Ballpark numbers, LEDs forward biased, somewhere between 1.4 and 2.5 volts. Varies a little bit on the current through it, varies with the wavelength color of the light. Okay, so generally when I'm working with LEDs, I usually, assume a voltage somewhere between 2 volts to 2.2, somewhere in there, as a ballpark number. Standard LEDs, the long side is the anode. It also has, you can't see it quite here, but there is a flat. There's a flat right, because looking at it from the end, there's a flat on this side. So the short end's the cathode, and the long side is the anode. Okay, if you're working with your breadboards, this is the package style you're going to be looking at probably, but they do come in other styles, right? Depending on the application needs and how much current. It's largely due to how much current. So the more current the diode has to handle, the larger the package style needs to be. This is a power diode. This is actually threaded. So this is going to be screwed into a aluminum heat sink, and this is going to be the heavy wire is going to be soldered on. These are various types of surface mount devices. They're very, very small, but they all work the same way. And I guess that's it. Thanks for watching. Catch you soon. Bye.